and parameters of the transistors and other circuit elements, which uh, which uh, uh, which will be providing or giving the functionality which we require, right? And to design these things, we use these tool flow and or EDA tools. And this is not one single EDA tool that we use, right? It is not that there is a tool which simply gives the functionality, it will give me a layout. It is not like that. We use tens of 50s or hundreds of various tools in the design flow to achieve this, right? So we break the basic task of designing a chip into small steps and carry out in the flow, and at the end we get a chip, we get a layout, right? We get a layout which we call as GDS, and then that GDS goes to the foundry and the foundry fabricates it, right? This is how the EDA tool flow works, right? So in this EDA tool flow, what we have is the system level design at the top. Then what we have is RTL to GDS flow, right? RTL to GDS flow, in which there are two basic steps. One is the logic design, and the second is the physical design. So in the logic design, we design we have a process through which we take an RTL. RTL is something which we write in Verilog, right? So do you know what is a Verilog? Yes, students at the back. Yes. What is a Verilog file? Do you have any idea? No idea? Okay. So Verilog file is basically a way in which we give information to the tool that what the design will perform. It is a behavior description of our, right. So now the for given a behavior description, what we do is the behavioral description, we take it through the various tool, and finally we get a net list. That is what the logic design process is. And then we have from that net list we get a layout, right? From that net list we get a layout, and that is the physical design, right? And then the GDS goes to the foundry for fabrication, right? And in this process we also have verification and test and diagnosis. So this is a complicated process, and therefore we need to do a lot of verification to ensure that things work as expected, and so on, right? And also we need to test whether there are any manufacturing defect or so on. If there are the defects, then we do not allow that chip to go to the end user and discard them, right? So the testing process is also very important, right? Okay, now why do we use machine learning in this flow, right? What is the motivation of using machine learning in the EDA tools, right? So the first thing is that during the design process, there are various abstraction levels, right? So at the initial stage we have lots of abstraction, meaning that there are lots of design details which are missing, right? And the design progresses, the details are added, and we and the abstraction decreases, right? Now when we are at the higher level of abstraction, what happens is that we have less information about the design. Nevertheless, we need to take some design decisions, right? For example, we have written an RTL code, right? And RTL code needs to be synthesized, right? Now, by synthesis means that in the RTL code we write something like y is equal to a and b, right? Now, if we write something like this, then this will be synthesized to an AND gate. You have A, B, and Y, right? This will be synthesized to this kind of circuit, to a netlist. But to do this synthesis and to get this AND gate, there are many choices available for a for a design tool. For example, what should be the size of this AND gate, right? It should be, or what should be the, how many transistors it should use, what should be the size of those transistors, right? So these types of design decisions needs to be made during, say, logic synthesis, which is at the higher abstraction level. But what happens is that this decision may not be correct information about the wires and other things. And when we look into those information, then what decision we have taken at a higher abstraction level, that will seem unoptimal or suboptimal. Right? So this is an issue with the design flow that we have. That we have to make decisions based on certain estimates, and those estimates can go wrong when we go down the flow, right? So in this case, what one of the motivation of the using ML technology in EDA tool flow is to make a better estimate of the design parameters, right? Now much better because ML technologies are basically more in VLSI is very large, right? This is the data that we need to handle in VLSI is very large. Just if we look into the number of the transistors that we have in today's world, right? That is, if we look into, say, Apple's ARM-based M1 Max SoC, there are 57 billion transistors. The level of scaling, right? So someone was talking about scaling from LSI to VLSI, right? And what will be the next one, right? So after VLSI engineers have actually stopped giving names. Now, VLSI was there when in the 1980s, 90s also. But after that, we have stopped giving names, and even if you have, say, transistor circuit or the integration in which you have 57 billion transistors, we still call it as VLSI, right? Because we know that this trend is not going to stop it. It has the scale of integration will go on increasing, and we do not know the limit at all, right? So giving name as VLSI, or people came with the term ultra ULSI, right? But no one accepted that term, right? People call now everything above, say, 100K as VLSI. Right? That is what we do. So the basic idea is that the number of data or the volume of data that needs to be handled in VLSI design is too high, right? And if we look into the number of transistors, or if we look into the models of the transistors also, each individual transistor, if we look into each individual transistor and do the simulation of those, right? And for simulation, we use various kind of model like PC model and so on. The model contains itself 400 parameters. Now you can think of 400 parameters, 57 billion things, how big the data is. Right? Now, for this kind of big data handling, the ML techniques are very good, right? They can discover the dependencies shapes and patterns very well, right? Which can is not very easy to do using deterministic techniques, right? So the large data can be handled well by ML technology and using statistical techniques and very powerful techniques. Sophisticated algorithms can be designed, or smart algorithms can be designed, which can yield much better solution or much better design, which will give a better results to us, right? This is the second motivation of using ML technology in EDA tool flows. And what is the third? The third is the transformations, right? Now, as I showed you the design flow, it started with the idea, finally ended up with the layout, right? And in between you had netlace, RTL, and other things, right? So the what it means is that in the design flow, our design goes through many types of transformations, right? So these transformations can be either domain transformation from, say, behavior to logic, logic to netlist, netlist to layout or transistor. So the domain is being transformed from top design flow, right? And the second thing is that data is being refined as the data as we go through the design flow, then the data gets refined and refined. For example, at the level of RTL, we just write A and B. There is no concept of sizing of the transistor at that point of time. But when you have a netlist, you have a cell instantiated for that, and you have a more information, or your data has been refined with the transistor size. And then later on, when you make the layout, you make the connections and interconnects. Now your data is further refined, right? So it means that as the design goes from the top of the flow to the bottom, right, data goes on refining, and the domain is being transformed and so on, right? So this is, now in this context, what happens is that the ML technology can give us a better solution. Right? Now, how do we evaluate a better solution? Right? How do you say that this solution is better than the other? Right? Okay, the students at the back. Yes. I assume that you are looking at your mobile. That is fine. That is fine. Now, can you tell how do you say that my mobile is better than the other mobile? What parameters do you think? Yes. Yes. Processor. Yeah, software. Yeah, software. Right? Your software is better than your friend's mobile software. What other criteria you can say that my mobile is better than my friend's mobile? Yes. Money. Soft. Cost should be less. Right. And good answer. Good answer. Next. Yes. It should download the internet very fast. Right. It should have support 5G. And camera should be very good, right? Battery backup should be very high, right? Emulated display, right? And what? Right. It should do multitasking, right? So all these things are known as figures of merit. These are known as figures of merit. Now let me take this problem to another level. You told this is what you want from your mobile. Right? Now as a designer, suppose you are designing your mobile. Suppose that. Forget about what you are browsing right now. Suppose you are want to design that mobile. Now to achieve this, what hardware should you have? For example, which processor you should choose? To understand that inside the mobile there will be a processor, right? Now which processor should you use? Why do you use? You are correct. You want to use Snapdragon. But why do you want to use Snapdragon? स्मूथ चलता है उसके लिए क्या फिगर्स ऑफ मेरिट ये बताइए स्मूथ का क्या मतलब है ये बताइए मल्टीटास्किंग कर सकते हैं एक बार बहुत सारा काम कर सकते हैं और फास्ट कर सकते हैं उसी का मतलब है ये परफॉर्मेंस जो है वो बोलता है कि कितना फास्ट चलता है चिप कितना फास्ट चलता है और दूसरा आपने बोला कि बैटरी कम खाएगा ये चाहते हैं आप अपने मोबाइल से। उसके लिए जो फिगर्स ऑफ मेरिट उसको बोलते हैं पावर। वो पावर कम से कम लेना चाहिए, राइट। और क्या फीचर होने चाहिए? कॉस्ट कम होना चाहिए, पॉकेट में जो है हैवी नहीं होना चाहिए,
लाइट वेट।
ज्यादा, राइट। दैट इज व्हाट इज एरिया। जितना आपका एरिया, चिप का एरिया कम होगा, कॉस्ट उतना कम लगेगा। क्यों कम लगेगा? क्योंकि एक ही वेफर से आपको बहुत सारे डाई निकल जाएंगे, इसलिए आपका कॉस्ट कम हो जाएगा। और क्या होना चाहिए आपके चिप में? बताइए। स्मूथ चल रहा है। स्मूथ चलने के लिए क्या चाहिए? खराब नहीं होने चाहिए। दैट इज व्हाट इज मेंट बाय रिलायबिलिटी। रिलायबिलिटी का मतलब ये होता है कि जैसा परफॉर्मेंस आज दे रहा है वैसे ही 2 साल के बाद भी यदि वैसा होता है तो यू से दैट इट इज अ रिलायबल, योर चिप इज रिलायबल, राइट। एंड देन टेस्टेबिलिटी। टेस्टेबिलिटी का क्या मतलब होता है? बताइए। अच्छा ये सोचिए कि आपके पास जो मोबाइल आया है, यदि किसी ने भेजा है, मान लीजिए सैमसंग वाले ने भेजा है, अपने स्नैपड्रैगन प्रोसेसर लिया है, वेदर दैट चिप इज वर्किंग करेक्ट और नॉट, क्या ऐसा उसने टेस्ट किया होगा या नहीं किया होगा? आपको ऐसा लगता क्यों है कि किया होगा? आपका एक्सपेक्टेशन किया है कि नहीं किया, आपको कैसे पता?
तो उसकी बेटर क्वालिटी देखने के लिए।
उसने किया है कि नहीं किया, ये आपको कैसे पता? और किया है तो क्या किया है टेस्ट, राइट। ये कंसेप्ट है टेस्टेबिलिटी। एक चिप होता है जो ज्यादा टेस्टेबल है, मतलब कि उसकी टेस्टिंग ज्यादा एग्जॉस्टिव हुई, मतलब उसके ज्यादा चीजें ट्राई करके देखा गया है आपको भेजने से पहले। और दूसरी की टेस्टेबिलिटी कम हो, उसमें कम पैटर्न्स किए थे और उसने पूरा फीचर्स को टेस्ट नहीं किया। दिस इज व्हाट इज द मीनिंग ऑफ टेस्टेबिलिटी। आपको दिखता नहीं है, लेकिन जो चिप डिजाइनर है उसको कंसर्न होना पड़ेगा कि मेरी चिप टेस्टेबल भी होनी चाहिए। So these are the figures of merit. And finally schedule. शेड्यूल का क्या मतलब होता है?
एक प्लान में वर्क करना।
Right. The schedule means कि you have a time. Right. Now if you think of yes, अभी आप स्नैपड्रैगन ले रहे हो, ठीक है, that is the best. But अगले एक साल के बाद भी यही वाला बेस्ट होगा या कोई दूसरा हो जाएगा? दूसरा हो जाएगा, है ना। उसके बाद एक साल के बाद
फिर और
तीसरा हो जाएगा। इसका क्या मतलब है? आज मैंने यदि एक प्रोसेसर निकाला, एक साल के बाद हमें एक नया प्रोसेसर निकालना पड़ेगा। नहीं निकाले तो कंपटीशन दूसरे स्नैपड्रैगन के बदले दूसरे ले लो। So for the chip designing company, you have to have a schedule to meet under a tight time to market. Right? This is what is the meant by time to market. So you have to design your chip within a certain schedule, meaning that you cannot exceed beyond a certain time to design. You cannot say कि मैं डिजाइन करने में 1 महीना नहीं 4 महीना लगेगा। ऐसा करिएगा तो आप मार्केट में किल हो जाएगी। कंपटीटर अपना मार्केट पे ले आएंगे और you will lose business. So these are the figures of merit. Now in achieving these figures of merit, the ML technology are much more effective than the traditional technology. Why? Because it is in ML methods, we can the tools can learn by examples, right? It can learn by examples, and it can explore the design space more exhaustively, right? Now, when we try to achieve these things, these are figures of merit. What it turns out is that these are working in different directions. For example, if you try to improve performance, then your area can go increase, राइट, मीनिंग दैट एक चीज आप अच्छा कीजिएगा तो दूसरा चीज
खराब
खराब हो
हाँ
जाएगा, right? And so this is what is known as trade off. This is the trade off you have to make. As a designer you have to think that which is more important, which is less important, right? And this trade off can be done in a more effective manner if we use ML technologies, right? That is why, because it can explore the design space in an efficient manner by looking at the past historical data and analyzing that, and can find out a better solution in less time, and you can meet the design schedule. So these are many of these things are currently done manually, right? But with the help of ML technologies, and these things can be automated, and automatic design exploration can be done. So this is the third reason why ML technologies can be used in design flows and can improve your design or make your design smarter. Okay, any questions till now? If you have questions, please feel free to interrupt. Okay. Now, which are ML techniques commonly used in EDA? Right. So, how many of you know about machine learning? No one? Okay. So, the ML techniques or machine learning techniques that are used in EDA is what is known as one is known as supervised learning. What is supervised learning? Any idea? See, this is very simple term, right? Supervised learning is the way learning in which a student has got a supervisor, right? That is what a very layman term of explaining. Supervisor means in this case are labels, right? Suppose you have lots of data, this geometric information, lots of shape. Then what you do is that you tag each shape with label. For example, this is an hexagon, this is a square, and this is a triangle, right? So you tag various elements or label the data with some label, right? And then use it to train the model, right? And using this train model, then when you give some data, unknown data, then based on its algorithm, it can predict whether it is a square or a
triangle
triangle. So the basic idea here is in supervised learning is that you are giving labels and data together for learning, right? This is what is supervised learning, right? And we can use supervised learning in the design flow to predict design parameters based on historical data like power, timing, and area, right? Because historical data, we will have information of design attributes and the corresponding power, timing, and other information. We can give the collectively this information to the ML tool, and ML tool can learn it, and based on that, later on they can predict and give us the answer. All right. Then there is the other is the unsupervised learning, right? So in we can also use unsupervised learning for in EDA tools. So what is meaning of unsupervised learning? So in unsupervised learning, we simply give data. We do not give labels. Now this tool, which is this ML tool, what it will do is that based on this input data and some statistical analysis, it will learn on its own to do a kind of classification. Right? For example, it can do clustering, and based on the statistical information gathered from here, it can differentiate between these three categories. Right? And in EDA tools, we can use this to detect anomaly. Right? For example, we give normal circuit and some and an abnormal circuit. When it is given, then based on the statistical inference done for the normal circuit, it can say that okay, this circuit has a problem, right? So with and without labels, we can the learning can happen and the tool can give us the answer. The third thing is reinforcement learning, right? Now, what is reinforcement learning? Again, this is a very simple way. Okay, so let me ask a very easy question. Yes, students at the back who are busy in the mobile. Yeah. So can you just tell if you want to train a dog, what do you do? क्या करेंगे बताइए. एक डॉग है आपके पास, उसको ट्रेन करना है बैठने के लिए. बहुत पहले बोले तो बैठे, घुटने को बोले तो कैसे ट्रेन कीजिएगा. हाँ हाँ उसे टास्क देंगे और वो करेगा तो फिर रिवॉर्ड देंगे. ठीक है तो आप बोलो कि बैठ जाओ. वो बैठ गया तो उसको आपने रिवॉर्ड दे दीजिए. आपने बोला बैठो, उसने बैठने के बाद रोल करने लगा तो आप बोलिएगा कि हमें रिवॉर्ड नहीं है. राइट. This is what of reinforcement learning. You are correct. You are correct. This is what is actually done in softwares, in tools also. So you have an environment. You have an environment based on environment. This agent, which is dog or your algorithm, it does an observation and it produces an action. If action is favorable and what you wanted is there, then you give a
Reward.
reward. Right? And if not, then you don't give a reward. Right? So this is what reinforcement learning is, and it needs a lot of examples. And once this is done many times, you need not worry about reward now. Now after that, whenever without giving your reward also, if you tell your dog to sit, it will sit. It will not do a rolling. Right? Initial phase reward is essential, but later on reward is not.
Essential.
So this can be used in EDA tool flows by for the application in the application in iterative design processes such as placement and routing optimization. Right. So these are some of the techniques that we use in EDA tools. Right. Okay. So how much time do I have in this?
Bus.
Sorry. You want a break? I don't know.
Yes, sir.
So, I don't need a break. I just want to check on the time. Depending on, I can modify the content, right? I will go to the more important thing and leave out the rest. Till 1 o'clock, I can go, right? So, what is the time right now?
5:17.
So, 45 minutes I have, right? Okay. So, I think I'll be covering most of the topics by then. Okay. Now, what are the key areas where we can use this ML techniques, right, in EDA, right? So, yeah, reinforcement learning. Okay. So, huh. Which one? Sorry, I didn't get your question. हाँ हाँ वो कुछ और क्या है वो मुझे बताइए. So I know of this agent based, right? So you have an agent and you have a reward, right? And based on your action, your reward gets changed, right? And that modulates your internal weights and other things, right? So inside this agent, you will have a model, right? Or you may not have a model. That is what I guess the other could be. Now this model can be say ANN or anything, right? Now based on the reward, the weights inside these models are changed, right? For example, if you have an NN, you have neural networks, right? NN is an artificial neural network, and these neural nodes are connected using some weights. Now depending on what reward you are getting, these weights will be modulated in with each of the iteration or each of the examples, and these weights move in a certain direction such that the reward is maximized, right? So this is the whole idea of this reinforcement learning. Okay, so what are the application areas
Like
machine
intelligent
learning in EDA tool
execution
flows, right?
algorithms,
So we can use it for, or we, yeah, so we can use in design implementation, right? We can use in system level design, we can use in logic synthesis, we can use in verification, we can use in test diagnosis and validation, and so right. So in the system level design, we can use it to estimate power, performance, and so on. Yeah. अच्छा, this fine. Okay. So we can use system level. So we can use machine learning in system level design for to estimate power, performance, and other figures of merit. We can use it for intelligent design space exploration, and we can use it for dynamic system level decisions, right? So these are some of the areas where ML techniques have been tried, right? Have been tried and are being researched to use, right? And in the logic and physical design, logic synthesis and physical design, it can be used for design recommendation. So we'll see a few examples of this in detail in the later part of this lecture. I'm just giving a summary right now, right? And we can use it to estimate cost of solution. We can use it to predict and fix violations, right? In the verification, we can use in simulation to fill verification holes. We can use it to speed up. We can use for technology libraries to have a better models. So we will be looking into this in the later part of this lecture. And then in test and diagnosis also we can use it for various purposes. Right. Now, since this ML technology is very powerful, all these commercial EDA tools take help of it, or they have proposed some solution or proposed some tool which uh, employs these technologies. Right. For example, do you know a name of a few EDA tools? Cadence, right? Any other? Synopsys. Right? These are two companies, right? So it's Cadence and Synopsys are the biggest companies of this EDA, right? And they have various tools for it, right? For example, Cadence will have Innovus, Tempus, and so on, at various tool set. And similarly, you have Prime Time and many very and Design Compiler and ICC Compiler and so on for Synopsys. Yeah, so Xilinx Vivado is another, right? So they give the board also and also the tools and so on. Then the third one is the Siemens EDA, right? Siemens EDA or Mentor Graphics, which are earlier, right? That is also. So these big two companies have launched their products, right? For example, Synopsys has launched the product or the tool which is known as Design Space Optimization AI or DSO.ai, right? And Cadence has come up with a tool which is known as Cerebrush, right? Which is intelligent chip explorer, right? So these tools basically internally use the reinforcement learning, right? These two use reinforcement learning, and it can start from an untrained model and optimize in successive iterations. And basically what they do is that they observe the designer itself, right? Based on the designer's decisions, old and the current decision, they try to manipulate and give suggestions to the designer that this will be better useful or better or worse, right? So these kind of things, these are the or these kind of capabilities are now available in the tools, right? Going forward, these technologies will become much more available, and people will be using or the designers will be using these ML technologies in the design flows. Okay, any questions till now? Now we'll take a few case studies, right, in which we are using ML technologies and to for you for the improving design and so, right. So the first one is our tool which is known as Lee. right? And it was a very old tool, right? In the 1990s, this tool was suggested, right? So this is known as learning apprentice for VLSI design, right? Of course, at that time, the hardware or the processing power of the computers were now not as high as now, right? Several orders of inferior to what we exist today, right? And therefore this kind of thing which was launched in 1990 couldn't take off because the processing power was not that at that point of time. But let us look into that what this tool used to do, and if we use the same thing now, it will work. Why it will work? Because the processing power of the computers and the compute resource has increased exponentially in last 30 years, right? So in this learning apprentice, what was there, that this there is a tool, right? This tool, what it does is that it is just observing the designer. This is the designer which is making your circuit, right? It is just observing that designer, and from the what the, for example, there is a problem to make a for adder, right? Now this what this designer will do is that pick the transistor, put in the layout, do the simulation, and so on, right? It will do those tasks, and this apprentice will simply looking at it and analyzing that data, right? So it acquires knowledge and learns rules by observing a design, right? And then it analyzes the problem solving step during their activities, and then after looking into these things, then it will analyze the that what step the designer took at this point. What was the problem, what was the solution, what was the problem, what was the solution. It will go on doing this kind of thing, and it will later on what it will do is that after sufficient reading or the observing the designer, it will start giving advice to the design, right? So you have this problem, do this you have a problem, do this, right? So it will start giving the advices or suggestions to the designer. Now the designer can accept that or reject that, right? It is up to the designer. If the suggestion is correct, they will accept, or not, then the designer will carry out the transformation on itself, right? So this is a kind of feedback which the tool captures. Whether its learning was proper or not, it can treat it as a reward, right? If the designer takes the suggestion and utilizes it in the design, then it is a kind of a reward, right? And based on that, it will update its database or the algorithm and or the weights and so on. So when a designer ignores the advice, consider it as a training sample and updates its rule, right? And given sufficient example and this kind of thing, it will start coming up with the correct suggestions, right? So this is the whole idea of that how the automation can be, or how the tool can, or the machine learning can be used to help the designer in taking decisions. Another case study that I'll show you is from our research group, right? So when we do this designing, right, now this designing is done with the help of libraries, right? So these libraries contains the timing models. Now these timing models are typically two-dimensional or three-dimensional tables, right, in which you have some information. For example, you have the input transition, you have the load. Based on that, you have a delay or the output slew and so on. So you have a kind of a database which is a table based, right? Now, because that it is a table based, it cannot have too many dimensions, right? It cannot, otherwise your library will become so bulky, it will be difficult to and to do the processing and so on. So in that case, what the tools use is a simplified delay model. What I mean by simplified delay model is like this. Suppose you have an AND gate, right? And the tool is trying to model the delay of this arc. So if the tool is trying to model the delay of this arc, it will assume the side input to be held constant to a non-controlling value. So it will assume that it is at a value 1, right? That is non-controlling value. The side input is at a non-controlling value, and the main arc is having a transition from 0 to 1 or 1 to 0, and based on this the timing model is made. This is what is known as single input delay or single input switching model, right? Now what can happen in real life is that the transition can happen at both the input at the same time, and if that happens the delay model will have errors, right? So, ignoring the multi-input switching can lead to large variations in delay, and therefore, what we can do is that we can use machine learning to represent multi-dimensional data to model the multi-input switching case, right? So it fits easily with the existing design flow, and we have actually used it in our design flow for training purpose, right? So I'm going fast here because I think it seems that you are not able to follow or these things. So let's not waste time in this. So um, we can train the model, and based on the training we can see the errors, and based on that we can do take various kind of decisions, and we see that there are good or low values of RMSE that we can achieve using these things, and this is more powerful than general techniques, because this is when we try to model multi-input switching, then there are so many transitions that it is not easy to model them using the traditional models, right? And therefore multi-dimensional dimensional information is useful here, right? Similarly, I think we have used it for congestion prediction. I'll go again fast here, right? Because I think the audience is not able to appreciate this, right? Again, this is something which Google has tried, and they have shown good results, right, for chip planning, right? This uses reinforcement learning. Yeah, so I think I don't it looks like the audience is not able to appreciate this, so I'm going very fast. So these are some of the challenges, right? Challenges in the using ML technologies in our EDA tool flows, right? These are some of the promises, right? Okay, so the conclusions are that ML technology is very powerful. It is very useful, right? You can use it for the smart design of chips, right? Okay, so these are the references. So this is the book from which I have taken materials, some of the materials, right? And these are some of the other references. These are the collaborators and the industry partners which I work, right? These are my research students. Okay, thank you very much.